Okay. Um, Hi everyone. My name is Kate, and welcome to the Astrobotany workshop. This is presented by Art Technically, which is a nonprofit based in Memphis that promotes STEM and arts education for K through 12 students by promoting free STEM and arts programming. Today, we're going to watch videos of Art Technically's Astrobotany workshop and do some hands-on activities with things from your activity box that was mailed to you. So make sure you have that activity box handy, and you'll also need a lamp, just like a standard household lamp to use for one of the activities. So make sure your parents get that for you and can help you with that. So let's get started. So I have a video. I'm just setting that up.
Hi, I'm Lily. I'm a workshop leader for Art Technically, which is a nonprofit based in Memphis, Tennessee, that promotes STEM and arts education for K through 12 students by providing free STEM and arts programming like this. I'm also a PhD student here at Rensselaer Polytechnic Institute, working at the Center for Lighting-Enabled Systems and Applications. Before coming to RPI, I worked as a software developer or programmer for the District of Columbia's Space Grant Consortium in Washington, D.C. While working for DC's NASA Space Grant Program, I met an astrobotanist, which is a scientist that studies growing plants in space, and he inspired me to go to graduate school to study plants. So this top left photo here is from 2019. It's from the last in-person NASA Space Grant Conference in Washington, D.C. before the pandemic hit. I'm pictured here with a couple other scientists that worked for the DC Space Grant Consortium at the time. At the top right over here, you'll see a photo of me from graduation last year. I graduated with a master's in lighting. I specifically looked at how plants interact with light, and that's what I research now. And the bottom photo is me in another lighting lab. And that bottom right one with the purple light, that is from my last in-person Astrobotany workshop. I'm very sorry I can't be there with you all in person, but hopefully with your activity kits, we'll be able to emulate that experience as best we can. So here at LESA, I study Controlled Environment Agriculture, or CEA. CEA is a method of growing food inside. When we grow food outside, like in fields, we can't control how much light the plants are getting, how much rain the plants are getting, or what the temperature is outside. So when we grow food indoors, we can control the plant's environment a little bit more. The three main ways we might control a plant's growing environment are where we grow the plant, such as what kind of soil the plant is grown in, the climate, which might include the temperature and the amount of water the plant gets, we're counting it from rain, and the lighting, which may include the sun or electric grow lights. There's a wide range of agriculture and controlled environment agriculture depending on how much we want to control the plant's growing environment and what in the environment we want to control. Many edible plants grow without any human intervention. For example, if you were to find a wild blueberry bush in the forest, that blueberry plant grew without any humans controlling its environment. But instead of gathering food from a forest, farming is a much more efficient way to grow a lot of food to feed our communities. Traditional or field farming is where most of our plant foods come from nowadays. On a traditional farm, you can control more of the plant's environment than you would in the wild, such as where the plants grow and how much of the plants grow, or how much you plant. Traditional farms are very common, so you've probably seen one or even maybe been to one. But if we want to control our plant's environment even more, we may choose to grow our plants in a greenhouse. A greenhouse is a glass or plastic building that can protect plants from colder weather. A greenhouse allows sunlight to reach the plants while protecting them from cold weather, rain and snow, and sometimes pests like animals and bugs. You may have also seen a greenhouse before, especially if you live somewhere that has cold seasons. If we want to control our plant's environment even more, we may choose to grow our plants completely inside in something called a vertical farm. A vertical farm is a building where plants are grown in stacks on vertical shelves in a completely controlled environment. The lighting, temperature, water, and more are all controlled by scientists in a vertical farm. Because the lighting, heating, and AC and water transportation all requires energy, vertical farms are very expensive to run. But some vertical farms can produce foods like tomatoes and lettuce, tastier, quicker, and more nutritious than traditional field farming. And in some places where it gets really cold or really dry, traditional field farming may not be possible in the cold or dry season. The lab I work in at RPI is focused on researching controlled environment agriculture for vertical farms. So here's a quick tour of our plant lab here at RPI's LESA Center. So here is our plant lab at RPI's LESA Center. This is our main area where we take measurements and analyze all of the plants that we grow. Back here is a dark room where you can see we're doing a grow light experiment over there. We also can take measurements of different light bulbs and lighting systems, and this equipment over here, that's an integrating sphere where you can put a light bulb in and measure how much light it gives out and what the kind of colors are. This is one of our recent grow light experiments. We've built this and now we're testing to see how the LEDs or the lights are performing. You'll notice that it's purple grow light, which is the kind that is in your activity kit. That sensor right there is measuring the lights above, and if you look all the way up, you'll see all of those LEDs shining down into this testing growth chamber. But I'll cover it back up so it can continue testing. And then we're going to walk over, here are our offices for LESA. And on the other side of our floor that we have at RPI, we have our growth chamber lab. This is where we grow all of our plants. Those big freezer-looking things are all of our different growth chambers. This one has sort of a greenish-looking light on it. You'll see that there's another sensor there testing those lights and some tomatoes that we're just storing up top. Here's another growth chamber. These are some pretty mature tomatoes that are growing under those LEDs. And then the next one is some more tomato plants we're growing. These are a little bit younger, so they haven't had any fruit yet. But I'll close that chamber up again so they can continue. This is the batch that we're going to be doing our measurements and analysis today. You'll notice that they are growing in water, not soil. There's no soil in our growth chambers at all. That's called hydroponics, and we'll talk about it a little bit later. Here's some little sprouts that are also growing in water, so you can see that. And here we have one of our lab techs is taking out these measurement sensors so that we can take all of the tomato plants out and do our measurements. We're going to drain all the water out so you don't have to carry the heavy water around. And here he's taking some chlorophyll measurements with that little machine right there. That little clamp measures how much chlorophyll is in the leaves. We'll take some photos of the tomato plants against this black backdrop just for record keeping sake, and then wheel them all the way over to that measurement lab I showed you earlier. And now the lab tech's going to prep to take our analysis and measurements of the plants, starting with some liquid nitrogen that we'll use to freeze the plants later. He'll take some different measurements on different machines we have, weigh all of the different parts of the plants, and then when he's done, he'll dip them in the liquid nitrogen to freeze them and store them in the freezer for record keeping sake. We hope you enjoyed the quick tour of our lab. There is one more scenario that is even more controlled than a vertical farm. That is astrobotany, or growing plants in space. When astronauts grow food on the International Space Station, or maybe one day on another planet like Mars, the food's growing environment has to be carefully and precisely controlled. Today, we're going to learn about astrobotany. Unfortunately, I can't be with you in person today, but our workshop leaders, Kate and Grace, can help answer any questions you have. And if you have any questions for me, you can have your parents help you email lily@arttechnically.org. If you haven't already, make sure to open your activity box. In it, you will find a copy of Leland Melvin's memoir called Chasing Space, an astronaut ice cream packet that we'll talk about later, some leaves and a light bulb that we'll use for a hands-on experiment, some stickers, and a paper packet with the title Astrobotany that you can use to follow along during our lesson. The only thing you'll need for your home is a standard lamp that you can put that light bulb into. The light bulb will fit into any standard household lamp, but make sure that you have an adult help you get the lamp and help you put the light bulb into it when we get to the experiment. You can open up your packet to page 6 and follow along with the next video. So, what is astrobotany?
All right. So, does everyone have their activity boxes opened? I'm going to assume you don't say anything, but that's a yes. Okay. Okay, I'll go ahead and play the next video.
So, what is astrobotany? Astrobotany is the study of growing plants in outer space. The word astrobotany comes from the base words astro, meaning related to space, and botany, meaning the study of plants. You might be asking yourself, why would we want to grow plants in space in the first place? Well, for the same reasons we grow plants on Earth, scientists want to learn how to grow plants in space for astronauts. Plants are very important to life on Earth. Plants provide us with food and oxygen, which we need to breathe, and being around plants can even make us feel happier. In outer space, there's not enough oxygen for astronauts to breathe, and there's no place that plants grow to provide astronauts with food. So for astronauts to have enough air to breathe and food for long space missions, being able to grow plants in outer space will be very important. So what do astronauts eat? When astronauts are exploring space, they need access to nutritious food. Launching things into space is difficult and expensive, so astronauts' food needs to be very lightweight, compact, very nutritious, easy to eat in microgravity, tasty, and last a long time without spoiling. It currently costs almost $3,000 per kilogram to send things to the International Space Station. The average person on Earth eats 2 kilograms of food per day. So if astronauts ate like they normally eat on Earth, it would cost $38,000 per week to deliver their food to space. Let's take a look at some examples of foods. An apple provides 5% of your daily needs for calories. Calories are a measurement of how much energy a food can provide you. An apple doesn't provide that much energy, but it does provide you with other important nutrients like vitamin C and fiber. An apple only weighs 150 grams, which is pretty light, but it doesn't provide you with much protein or fat, which your body also needs. Apples are very healthy and nutritious, and they're a great choice for a snack on Earth. But it would cost $500 to send one to the International Space Station. For $500, we might want to send astronauts something that has more calories per weight. Freshly picked apples only stay fresh for about a week, but when stored in a special environment, they can stay fresh for months. An apple would be easy to eat in space. It wouldn't generate crumbs that could fly all over the air in microgravity, and an apple is solid and stays together while you eat it. But apples are not very compact. 86% of an apple is water, so to reduce an apple's weight and make it more compact for space travel, we might freeze dry it. Freeze drying food is a great method to prepare food for space. Freeze drying reduces a food's weight while leaving the nutrients intact by removing all of the water from the food. Astronauts can take the freeze-dried food and reconstitute or rehydrate it by adding water. 2 factors determine whether a substance will be a solid, liquid, or gas: temperature and atmospheric pressure. You know that when the temperature gets really cold, water will take the form of ice and be a solid. And when it gets warmer, water will take the form of a liquid. And when it gets even warmer, water takes the form of a vapor and is a gas. You might have learned that the freezing point of water is 0 degrees Celsius or 32 degrees Fahrenheit, and that the boiling point of water, or the temperature when liquid water becomes a vapor, is 100 degrees Celsius or 212 degrees Fahrenheit. But the freezing points and boiling points of liquid depend not just on the temperature, but also the atmospheric pressure. The atmosphere that surrounds Earth has weight and pushes down on anything below it. The weight of air above a given area on Earth's surface is what we call atmospheric pressure. Generally, the higher you are, the less atmospheric pressure there will be. So the top of a mountain will have less atmospheric pressure than sea level. This is because that air has weight. The more air on top of you, the more pressure there will be. If you take a block of ice and heat it above its freezing point, 32 degrees Fahrenheit, while the atmospheric pressure is near sea level, it will melt into a liquid. However, if the atmospheric pressure is below a certain point, which is that yellow portion of the graph, the ice will be warm enough to thaw, but there isn't enough pressure for a liquid to form, so it becomes a gas instead. This process is known as sublimation. Just like evaporation, sublimation occurs when a molecule gains enough energy to break free from the molecules around it and change states. Water will sublime from a solid, that is ice, to a gas, which is vapor, when the molecules have enough energy to break free, but the conditions aren't right for a liquid to form. So sublimation is the shift from a solid directly into a gas, skipping over the liquid state. Freeze drying uses sublimation to release the water in foods as vapor. By skipping the liquid phase of the water in the food, it leaves the solid food particles intact. In your activity kit, you'll find a freeze-dried food, freeze-dried ice cream sandwich, otherwise known as astronaut ice cream. Make sure to ask your parents for permission to eat it so that they can read the label and make sure that you're not allergic to anything in the ice cream. Notice that the ice cream bar is still intact and looks just like an ice cream bar you get from the freezer, but all of the water has been sucked out of it, so it'll be crunchy. Let's look at some.
Okay, so if everyone wants to get out your astronaut ice cream, and you can go ahead and try that, or ask your parents if you can go ahead and try that. And let me know what you think about it. Let me know, do you think it tastes good? Does it taste weird? Is the texture weird? It has all of the water sucked out, so, that's going to be a little different. You can just in the chat. While everyone is doing that, I'm going to go ahead and start the next video.
Some more examples of foods in space. If you're following along in your packet, we're on page 7. A corned beef sandwich has a good mix of carbohydrates, protein, and fat, but not a lot of vitamins. While sodium is a necessary part of our diets, too much of it can be a bad thing, and a corned beef sandwich is very high in sodium. By weight, it would cost $517 to send a corned beef sandwich to space. A corned beef sandwich would be very difficult to eat in space. In microgravity, the 2 pieces of bread might fly apart if you weren't constantly holding your sandwich together. Bread also generates crumbs, which wouldn't fall down for you to sweep up in space. Instead, they'd fly around the air that you and your fellow astronauts are breathing, which could be a recipe for disaster. Corned beef only lasts a few days in refrigeration, and it would be difficult to package one for space travel. If you've ever opened up your lunchbox to an accidentally smashed PB&J, imagine how difficult it would be to keep a sandwich from getting smashed in a rocket ship. A corned beef sandwich would be one of the worst foods you could bring to space. But in 1965, on the Gemini 3 mission, American astronaut John Young infamously snuck a corned beef sandwich onto the spacecraft. Let's watch a short video about the incident.
Astronauts have to deal with a lot of dangers in space. deadly debris, harmful cosmic rays, and sometimes a corned beef sandwich.
Houston, we've had a problem.
In the 1960s, at the height of the space race, space food was either compressed into utilitarian packages or pureed into a tube. NASA did this in part to reduce the dangers free-floating crumbs could pose, like wreaking havoc on the space capsule's instruments. During the Gemini 3 mission, astronaut John Young didn't quite get the memo when he snuck a contraband corned beef sandwich into space.
Ooh.
Sure, the sandwich could have caused a life-threatening accident. But hey, wouldn't you want to know how a sandwich tasted in space? Here's how the event played out between Young and his co-pilot, Gus Grissom.
Elapsed time of 022825. Roll left, 55. What is it? Corned beef sandwich. Where did it come from? I brought it with me. Let's see how it tastes. Oh, smells, doesn't it? Yep, it's breaking up. Is it? I'm gonna stick it in my pocket. It was a thought anyway. Yep. Not a very good one.
And NASA and Congress didn't think so either. Young was reprimanded for his actions, but luckily for him, the incident didn't derail his career. He later was part of the Apollo 16 mission and walked on the moon. But that time he made sure to leave his packed lunch at home.
Tranquility Base here. The Eagle has landed.
More food together. A nutrition powder. A nutrition powder is specifically made to be extremely nutritious, providing adequate amounts of carbohydrates, protein, fat, and vitamins and minerals. A nutrition powder might be mixed with water, which you could drink with a straw. This would be very easy to eat or drink in space. Nutrition powder can stay unspoiled for over a year, and it is compact and easy to transport. 148 grams of nutrition powder, which is about a serving size, would cost $400 to transport to the International Space Station. However, nutrition powder can be not very tasty, and astronauts might not like to drink all of their meals. Next, we'll do another activity together. Think of some foods and look up their nutrition facts. See if they would make good space foods by analyzing how nutritious they are, how easy they are to eat, how much they would cost to transport by weight, and if you think they taste good. Your sense of taste is lessened in space, so spicier, bolder, or stronger tasting flavors may be better. On page 9 of your packet, you'll find this food analysis worksheet. Pick a food and Google the fill in the blanks for that food to analyze it. If you get stuck, you can ask Kate or Grace for help. Astronauts no longer
Okay, so you should all have your packets, either the ones you got in your box or you can follow along the link that Grace sent. And so on page 9 or 10, I think it's page 10, you'll have a little worksheet. So think of a food that you might want to take into space and do some research about it. Look some up how many calories it has, how many carbohydrates, protein, fat, and you can think of some other things like vitamin A, vitamin C. It'll probably be easier if you think of something like an apple or an orange rather than, a salad, which could have a bunch of different things in it or have, it could be a bunch of different sizes. It'll be a little easier to find information about a single food. So yeah, if anyone needs any help with that, you can ask any questions you have in the chat. Um, Ooh, that's a good question. Does the nutritional value of a food change in space? No, it wouldn't change in space. It would still have the same amount of calories or, sugar or whatever, whether it was on Earth or in space. Um, your ability to taste it though would change. So even though it would have the same amount of carbohydrates, sugars, whatever, it would taste differently to you.
I have a question, Kate.
Mm-hmm.
Um, would the nutritional value change if it's freeze dried versus it's not freeze dried?
I think some things would stay the same. Obviously, if you think about your ice cream sandwiches, your astronaut ice cream, all of the water has been removed. So it does not have all of that water. You're not getting, any water from it, but it still has all of the same um, sugars, flavor, things that it had before. I'm sure that you probably lose a little bit of stuff in the freeze drying process, maybe some of the material is lost, but I don't think it would change it drastically.
Okay, thank you.
Mm-hmm. Dehydrated foods like kale chips. Does the water content in our body affect salivating or hydrating dehydrated food? Another good question. Um, hmm. Think about this one for a second. It definitely, um, yeah, I think eating if you imagine eating all dehydrated foods, you'd probably have to drink a lot more water. You can get water from your food. Like if you imagine, lettuce or something, fruit, something that has a high water content. When you eat that, you're still getting some of the water that you require from that food. But if you're eating predominantly dehydrated foods, then you're not going to be getting your body isn't going to be getting water from that food. So astronauts probably have to drink a lot of water to make up for all of that. Because yeah, I think you would get pretty dehydrated if you only ate dehydrated foods. So mixed nuts. So uh, do you want some help looking up the calories and nutritional content for mixed nuts? Let me. So I'm just going to look up some random mixed nut pack and see. Okay, so here. So, according to Google, 1 ounce of mixed nuts has 173 calories, 5 grams of protein, 16 grams of fat, 6 grams of carbs, 6 grams of fiber, and then 12% of the recommended daily intake of vitamin E, 16% of your recommended daily intake of magnesium, 13% for phosphorus. Let's see what else it says. Oh. Yes, and then it has all of these different vitamins and minerals that you need. So if you just want to copy that, you can.
Hey, Kate, we have a question from Amina. She said, could you please put up the equation again for calculating the cost to bring a food into space? So I guess once she has that copied, you can switch back to the equation sheet.
Mm-hmm. So the cost to transport, it's the weight of the food in grams divided by 1,000, and then times 200 or 2,720. So I don't know how to access the chat in share mode. Wait, here we go. Okay. I'm going to go ahead and start the next video, just to make sure that we have enough time to get to everything.
Longer have to survive off of nutrition powders and cubes. Now, astronauts on the International Space Station enjoy a wide variety of nutritious foods. Here's a NASA astronaut's meal of shrimp, scrambled eggs, a granola bar, and M&M candies. Here, an astronaut has cooked up some ramen noodles from the Japanese Space Agency, or JAXA. Even if an astronaut's diet is nutritionally complete, it can be disappointing to not have any access to fresh foods. Access to fresh foods, like fruits and vegetables, improves astronauts' moods. Sending fresh foods to space from Earth is difficult and expensive, so it would be beneficial for astronauts to grow some fruits and vegetables in space to incorporate into their diets. Astronauts on the International Space Station have already started eating some of the lettuce they've been growing for experiments. It takes less than 1 day and costs almost $3,000 per kilogram to send things to the International Space Station, but it would be even more expensive and difficult to send things farther into space, like to the moon or to Mars. For astronauts to explore further into space for longer periods of time, it will be necessary to grow some of their food in space, and figuring out the best ways to do that is what Astrobotany is all about. As of 2021, it takes about 6 hours to get from Earth to the International Space Station, 3 days to get from Earth to the Moon, and 7 months to get from Earth to Mars. Plants not only provide us with nutrition, but they also improve our moods. Interacting with nature is essential to maintaining a sense of well-being. Spending time around plants can improve your mood and reduce stress and anxiety. There's no natural plants in space, which can leave astronauts feeling sad and disconnected from Earth. Taking care of plants can help astronauts increase their quality of life in space and boost their morale. Space habitats present the toughest possible challenge for ensuring safe, breathable air, since they're entirely closed systems in an airless vacuum. On Earth, plants clean the air through the process of photosynthesis. As humans breathe in oxygen and breathe out carbon dioxide, plants do the opposite. They absorb light, carbon dioxide, and water to generate sugar, which can become food for us, and oxygen, which we need to breathe. Using plants to provide astronauts with oxygen in space will be an important part of long-distance space travel. Plants need a few things to live and go through photosynthesis: carbon dioxide, water, light, and something to grow in. Photosynthesis is the process by which plants make their own food, sugar. Carbon dioxide is a gas that humans and animals produce as a byproduct of their cellular respiration. During photosynthesis, carbon dioxide passes through small pores or holes in the plant's leaves where it is absorbed and used. Plants also need water to live. Water is absorbed by the plant's roots and passes through vessels in the stem on its way to the leaves. Water helps move nutrients into the plant. When a plant is properly hydrated, there is enough water pressure to make the leaves strong and sturdy. When a plant doesn't get enough water, the pressure inside the stems and leaves drops, and they wilt. As water evaporates from the leaves, more water is pulled up from the roots. Plants also need a growing medium. A growing medium is the material used in the container or the ground to grow a plant. The growing medium provides a plant with necessary nutrients such as nitrogen, phosphorus, and potassium. The most common growing medium is soil, but scientists have found ways to grow plants with no soil, using only water saturated with nutrients plants need. This growing method is called hydroponics. Astrobotanists grow plants hydroponically because hydroponics takes less space, hydroponics can be faster, and it is difficult to transport nutritious soil to space. Plants can get all of the nutrients they need from special water and air, eliminating the need for soil. But growing plants hydroponically is more expensive than growing them traditionally because the nutrient blend for the water used to grow the plants must be specially formulated and monitored. You need special facilities like greenhouses or labs to grow plants hydroponically. The special facilities may need supplemental lighting, which is lighting other than the sun, which is expensive. And the facilities take a lot of energy to maintain. On Earth, some foods are grown hydroponically because it is cost-effective to do so. Tomatoes and lettuces are the most common foods grown hydroponically. Next time you go to the grocery store, check the tomato section to see if any tomato containers say hydroponically grown. You might find one. Tomatoes and lettuces are cost-effective to grow hydroponically because the nutrients they need are easy to provide via nutrient blends for water. They grow quickly and can be grown in vertical farms. And they tend to taste better when they're grown hydroponically since they can be delivered locally instead of flown in from another country. A plant like wheat is extremely difficult to grow hydroponically, so it costs more to grow wheat in a hydroponic space than in a field, and consumers are not willing to pay for that extra cost for wheat. In space, there is not an option to grow plants traditionally. Some scientists study how plants might be grown on other planets or celestial bodies such as the Moon and Mars using soil, but lunar and Martian soils are not very nutritious, so engineering these soils to work for Earth plants is really difficult. So, most astrobotany experiments focus on growing plants in space hydroponically. Some plants grown hydroponically in space include lettuce, cabbage, onions, radishes, and bok choy. Light is also required for photosynthesis. Traditionally, plants get all the light they need from the sun, but in space, it might not be possible for sunlight to reach plants astronauts are growing. Instead, astronauts use electric lighting or grow lights to grow plants. Radiation is energy that travels in waves or particles. Radiation is all around us in many forms. The electromagnetic spectrum describes radiation by how big its waves are. Radiation with longer wavelengths may include radio waves and microwaves. Radiation with shorter wavelengths may include X-rays and gamma rays, which can be harmful to humans. The portion of the electromagnetic spectrum between 400 nanometers and 700 nanometers is called the visible spectrum. The visible spectrum is radiation that we can see. The shortest wavelengths we can see look purple, and the longest wavelengths that we can see look red, and there's a rainbow of colors in between. Infrared radiation is a bit longer than the red part of the visible spectrum, and it makes up heat. Ultraviolet radiation is a bit shorter than the purple part of the visible spectrum, and it's what gives us sunburns. Ultraviolet radiation can also be used to disinfect things by killing certain germs. The visible spectrum is just the portion of the electromagnetic spectrum that humans can see. Other animals can see or absorb different parts of the electromagnetic spectrum, and plants use different spectra too. The spectrum that a particular organism can see or use is known as the organism's action spectrum. Most plants' action spectra peak or absorb the most radiation at the blue region, around 450 nanometer wavelengths, and at the red region, around 670 nanometer wavelengths. This means that plants need a lot of blue light and red light for photosynthesis, but not a lot of green light. The sun provides a lot of all colors of light, but to be the most efficient, grow lights usually just include a blue light and a red light, which looks like a purple light to humans, because blue and red make purple. Here's a photo of a grow light. Notice the LEDs on the grow light, those light dots at the top, are either red or blue, which generates purple light when put together. The sun and most lights in our buildings produce white light. White light is a combination of all the colors of the visible spectrum. When you shine white light through a prism, the prism can separate the different colors that make up the white light, producing a rainbow. When a white light shines on the plants absorb red light and blue light for photosynthesis, and most of the green light is not absorbed, so it bounces off the plant. This green light that bounces off the plant is what you see, which is why plants usually look green. In this diagram, a white light made up of green, red, and blue spectrum shines on a plant. The plant absorbs the red and blue light for photosynthesis and emits the green light towards your eye, and you see green. For our next activity, you'll need to get your grow light bulb and your fake plant leaves from your activity box. Have an adult unplug your lamp and screw in the purple grow light bulb that came in your box. Then the adult can plug in the lamp and turn it on. Be very careful not to look directly at the light since you don't want to hurt your eyes. With the lamp off and the other white lights in your home on, notice that the plant leaves appear green. That is because white light contains all colors of light, including red, blue, and green. The plant leaves absorb the red and blue parts of the white light and emit the green parts of the light, which bounce into your eyes, allowing you to see green. When you're ready, turn off all the lights that you can except for the purple grow light. Observe the plant under the purple light. What color does it look? When you place the green plant into the purple light, you should see that it looks dark or black, not green. This is because the plant absorbs the red and blue parts of the light, but there is no green in the purple light to bounce back into your eyes. You can also place red, blue, or purple things near the purple light to see what color they appear. If you're following along,
All right.
plants need a few things to live and go through photosynthesis.
So, everyone, get your purple light set up. But while you're doing that, I have my own, and so I can do a little demonstration. So right now, as you can see, I have white light. I have a window open, so just natural light from the sun, and everything, looks normal colors. And I have a plant right here, and it looks green, obviously. This is a little basil plant, so something that astronauts might want to have in space to make their food taste good. But when I close the window and I turn on this purple light, if I hold it up to the purple light, it looks dark. It looks not green anymore, like almost black. Now I can kind of hold it away and you can see the green again coming from the white light emitting from my computer screen. And then back up here, it's very dark. and doesn't look green at all. So you all can try doing that. And then if you have anything else that you want to see what color it looks like, I have this little puzzle box right here. And in the purple light, you can still see that it's red because purple has red in it. But I don't know if I have anything interesting. This orange bottle still looks pretty orange. Maybe a little more red because orange is made up of yellow and red, and the purple light doesn't have yellow or doesn't have green light. So things can look a little strange. Okay, so hopefully you all are trying that out for yourselves. If you have any questions, you can put them in the chat. Okay, so we have one more video, and this session is supposed to end at 1:30, so I'm going to go ahead and play that.
If you're following along in your packet, we're on page 18. It isn't so easy being green. Electric lighting and hydroponic growing can be used on Earth to help grow plants, but growing plants in space presents even more unique challenges. Gravity perception is important to plants because they need to send their roots downwards towards water and nutrients, and their shoots upwards towards light. Plants use special cells to sense gravity. When plants are grown in microgravity, they may become confused and grow in strange ways. A plant like lettuce is less dependent on gravity, so it is easier to grow in space, but a plant like wheat may get more confused. Astrobotanists must find ways to help plants grow when they can't tell which way is up. There are also forms of radiation in space that are harmful to people and plants. Exposure to harmful radiation can cause health problems in both humans and plants. Space scientists have to engineer ways to protect astronauts and the plants they grow in space from this harmful radiation. There are many jobs in the space science field. Astronauts rely on a whole team of scientists and professionals to go to space. Astrobotanists study how to grow food for astronauts. Textile engineers design and make spacesuits. Software developers write code for space shuttles and rovers. You can explore all of the careers NASA has to offer on their Exploring Careers website, which we'll send in the chat. For our last activity, we're going to talk about Perseverance. Perseverance is a car-sized Mars rover designed to explore the crater Jezero on Mars as part of NASA's Mars 2020 mission. It was manufactured by the Jet Propulsion Laboratory and launched on the 30th of July 2020. Confirmation that the rover successfully landed on Mars was received on the 18th of February 2021. The parachute used to land the Perseverance rover on Mars contained a coded message. Can you decode it? Use the Perseverance worksheet to see the secret message from NASA scientists and engineers. You can also make a postcard from Mars by following the instructions in your packet. I'll get you started on the Perseverance worksheet so you know how to start, and our workshop leaders can help you more if you need anything after that. On the last page of your packet, you'll find the Perseverance worksheet. The Perseverance worksheet contains a secret coded message left by NASA scientists and engineers. In the secret coded message, there are 3 words and 16 letters. To decode each of the letters, we'll have to match up each of the blue boxes that are numbered to the values on the key over here. I'll get you started with the first 2. The first blue shape over here is number 1. We'll count what the color sequence looks like in this one. It's 1, 2, 3, 4 white, 1 red, and then 1, 2 white. We'll go back over to the key, and now we're looking for a letter that has the coded message 1, 2, 3, 4 white, 1 red, and 2 white. If you look at the key, you'll notice that D corresponds to that, with 4 white, 1 red, and 2 white, which matches our number 1 with 4 white, 1 red, and 2 white. So in our number 1 box over here, we're going to write the letter D. Well, we're going to try to write it better than I can. For number 2, we're going to go to the blue shape that's number 2, and we're going to do the exact same thing. We're going to count the color sequence. So it goes 1, 2, 3, 4, 5, 6 white, 1 red. So 6 white and then 1 red. We'll go over to the key and try to find the letter that has 6 white and then 1 red. We're looking at the key. You'll notice that the letter A matches that with 1, 2, 3, 4, 5, 6 white, 1 red. So for number 2, that answer is A. Now you'll keep going until you get to all 16 letters so you can get the secret message from NASA scientists. If you run into any trouble, have Kate or Grace help you. Thank you so much for participating in Black Families Technology Awareness Day at RPI and in our Astrobotany lesson. If you have any questions for me, including on how you can get further involved with space science, you can send them to lily@arttechnically.org. Parents, if you're interested in joining our mailing list to receive notices of virtual and in-person workshop opportunities for your student, you can sign up at our website, arttechnically.org/BFTAD. Or you can email team@arttechnically.org. We hope you had fun. And if you haven't signed up for Art Technically's Young Black Scientists and Engineers panel and Valentine's Day coding workshop, that will be held at 2:50 p.m. Eastern Time, and you can still register for it on the Black Families Technology Awareness Day dashboard. Thank you so much.
Okay, so we're technically out of time, but if you are able to stay and you want to work on the Perseverance code worksheet or have any questions on that, feel free. Also, if you have to go, that is fine.
Is it still recording?
Yeah. We